Hi students, in this video we will be studying the chemical structure of starch, that is what is the chemical composition of starch, constituent of starch. In previous videos we have already finished the polysaccharides, general constitution of polysaccharides. Now starch. What is starch? We say starch is basically a white tasteless solid carbohydrate which is having a formula of C6H10O5 whole N. That is a homopolysaccharide. That means the polysaccharide with one particular monosaccharide unit. Only one monosaccharide unit is there present in the starch molecule. So we say it is basically a storage compound in plants because it is generated in plants and it stores the energy for the plants. It is a storage compound in the plants and made of glucose units. And this homopolysaccharide is made up of two components. When we talk about the starch, we are discussing about two components which are main components of the starch. One is alpha amylose and then second is amylopectin. So we are going to study, while studying the structure of the starch, we have to study the structure of alpha amylose and we have to discuss the structure of amylopectin. These are the two constituents of this starch. We say the amylopectin, they are the two constituents of starch. When we say amylopectose, it forms around 10 to 30% of plant starch and is made up of 250 to 4000 D-glucose units which are linked through 1,4 alpha 1 bonded alpha 1,4 linkages. They are having a alpha 1,4 linkages. And then amylopectin, which makes around 70 to 90% plant starch and is made up of D-glucose units connected by, there are two types of connections when we say about this. One is connected by alpha 1,4 glycoside acidic bonds, and then we are again having a 1,4 or we can say the carbon 6 point C6 branch points in this the amylopectin case. So we will be taking it branch point, which will be taking it separately. So to discuss, when we say the alpha amylose, that is insoluble, that is not soluble in water, and it has the tendency to coil, it forms a helical structure. So to study the main structure of the chemical constitution of starch, we have to study the both alpha amylose as well as the amylopectin. Now, when we say the structure, main starch, the structure of starch, it has been found through various analytical data. It has been found that it is having an empirical formula of C6H10O5 and to the power n whole n, where n can be a number, that is the number of, we say that the glucose units or the number of these repeating units of C6H10O5, how many times these units have been repeated. Now on acid hydrolysis, when a starch was hydrolyzed with the dilute acid HCl, we are getting 98% of the glucose molecule. So this indicates that the main constituent of starch is glucose. That is, the starch is made up of glucose units. So we say that it is a homopolysaccharide, and this homopolysaccharide is having the monosaccharide which is present in it is D-glucose. Again, as in case of cellulose, we found that the D-glucose is main constituent. So here again we are finding that the D-glucose is main constituent. So in cellulose and starch, there is some the arrangement of glucose units to which they are, how they are connected and what is their arrangement, that makes it different from the starch. That makes starch and cellulose different to different substances. So when we are doing the methylation, as we know that methylation is done in using the methylating compounds like methyl iodide in presence of base, or methyl iodide in presence of barium oxide, or and DMSO. That was Srivastava et al. In 1963 who did it. And then we have another, that is dimethyl sulfuric acid, CH3 whole twice, SO4 So when we are using any of the three, that is the methylating process, it has been found that a tri-substituted product has been found. So that indicates that in the D-glucose, since we say that it is the main constituent is D-glucose, so we say in each glucose unit there are at least 3 hydroxy groups which are free in the starch. So these hydroxy groups have been converted into O-methoxy groups, OCH3 groups, and there's the formation of OCH3 groups. So this shows that there are almost two, that the two hydroxy groups are linked, and when it is in the pyranose form or furanose form, whether in pyranose form or furanose form, there will be at least 3 hydroxy groups which are free and the other groups are linked. So when hydrolysis of methylated starch was done, the product obtained was 2,3,6 tri O methyl D glucose and 2,3,4,6 tetra O methyl D glucose. That methyl D glucose was around 4.5% and the 2,3,6 tri O methyl D glucose was around 90%. So this 4.5% indicates that there is a chain length of around 30 to 40 glucose units present, which was, when it is also confirmed from that there are at least, when we say the methylated glucose, we say that the carbon 1, carbon 2, carbon 3 and carbon 6 hydroxy groups in glucose molecule were free and they were methylated. That means then the molecules, the carbons which were engaged in the ring formation is either 1, 4 or 5, because the 3 are now free, 1, 4 or 5. Again, in the second case, since we are obtaining 1 methoxy here, 2,3,4,6 tetra methyl D glucose, that indicates that in one of the minimum in one of the side glucose molecules, it is having the free methoxy group that is present at 1, at carbon 2, carbon 3, carbon 4 and carbon 6. They are free methoxy groups and they remain free. That is why they remain they remain connected. That the methoxy groups at these, they are having the methyl linkage. The methoxy groups, they were free in the starch, and now when methylated, they were methylated, and only the group 5 and here CHO. So we can say this is because of the pyranose form and they were engaged. So from here we can say that in starch, the glucose units which are present, they may be in pyranose form, which is also obtained by hydrolysis, which has been given on the basis of the hydrolysis, that is, they are not really hydrolyzed. So they are in the form of just a pyranose form. Then we say that there is a linkage type, and that linkage type is 1,4 linkage, which are present in these molecules. And it has been also found that since the 4.5% of the 2,3,4,6 tetramethyl D glucose, that is the non-reducing end of the chain, which produces us the 2,3,4,6 tetramethyl D glucose, it shows that the chain length should be around 30 to 40 glucose units. Now how we say that actually it has been found that this product is having alpha linkage. It was based on the formation of presence of maltose units. 2,3,6 tri O methyl D glucose and 2,3,4,6 tetra O methyl D glucose have been obtained, and this has been around the tetramethyl D glucose has been around 4%, 4.5%, and this was around 90%. It has been shown that the similar types of products have been obtained when methylated maltobionic acid, that is maltobionic acid, when it has been hydrolyzed, and the same products have been obtained. So we say that the starch is having similar structure to maltobionic acid. And maltobionic acid, we say that there is the presence of 1,4 link, the presence of the nature of the linkage which is present there, that is a alpha nature. The linkage is having an alpha nature. So starch is hydrolyzed. When starch, we have used the diastase enzyme to hydrolyze the starch, we are getting the maltose unit has been formed. The maltose units have been formed. So again, since the maltose units, we say that there is one there they are having 4 alpha linkages. The maltose are basically 4 alpha units. They are 4 glucopyronoside alpha glucopyronose forms. So they are again having the alpha forms. So we say that the nature of the linkage which is present there, that must be the 4. So we say since there are 4 linkages are present, and the nature of these linkages is alpha. Then glucose units, when starch is made of glucose units, we say that they are connected one by alpha 1,4 glycosidic linkages. That has been confirmed by the so far. So we say that the tentative structure of glucose must be like this, where we can have a non-reducing side and reducing side, and that this one is the reducing end, and we have the maltose units which are present in it, and we say n number of maltose units are present. So, and these rings we can say that when they are present in the pyranose form, you can see here that they are alpha linkages. If you watch this part, oxygen, the position of O ring oxygen and the position of the linkages, we say that they are having 1,4 linkage, and these linkages are alpha in nature. So as in the previous slide, we have seen that only the 4.5% of the 4.5% of 2,3,4,6 tetra O dimethyl glucose have been obtained. That indicates a chain length of around 24 to 30 glucose units. That was further confirmed by the N group analysis by Haworth, and it has been found that the molecule is having a linear molecule, and the glucose units which are present there, they are around 24 to 30. But when the viscosity measurements were from the viscosity measurements, it was revealed that starch is a highly branched structure. So we say that it might be. Then Haworth in Haworth later on said that then the 24 to 30 units may not be present. It may be more than that, because we are having a branched type of structure. So actually, to know the actual structure of the starch, starch has been separated in 2 components. One component is alpha amylose and beta amylose. Alpha amylose and not beta amylose. It is alpha amylose and amylopectin. Alpha amylose and amylopectin. So in this case, we can say that when starch was was dissolved in water at 70 degrees centigrade, and then N-butanol was added to the solution, and the solution was allowed to cool, alpha amylose was precipitated with N-butanol, and the remaining mother liquid which was there present, it has the amylopectin in it. That mother liquor was then treated with methanol, and with methanol, the second, it was this the amylopectin was precipitated out as an amorphous product by using the methanol. So we have N-butanol. In N-butanol, it was alpha amylose. It was soluble in the this N-butanol, because alpha amylose is insoluble in water, and then amylopectin, which is soluble part, which was present in the water, and that was then later precipitate as an amorphous solid using the methanol. So now, to discuss the nature of the structure of the starch, we have to discuss the structure of both alpha amylose and amylopectin chain. We'll say that what is the nature of the starch. Now, when alpha amylose, the structural elucidation of alpha amylose, the molecular formula of alpha amylose has been found as C6H10O5 whole N. That is an empirical formula. So we say that it is an N times C6H10O5 units are present in alpha amylose. So again, when acid hydrolysis was done using the HCl, it has been found that the main constituent of alpha amylose chain is again the D-glucose. So we say that the alpha amylose is the main constituent of alpha amylose is D-glucose. And when enzyme hydrolysis was done, alpha amylose, when used by beta amylase enzyme, has been used for hydrolysis, it has been found that alpha amylose gives the maltose units, the main constant of this. So we say that the maltose units are present. If maltose units are present, we say maltose units because that is an established this structure. It has been confirmed that maltose units indicate that there is a 1,4 linkage, glycosidic linkages are present in alpha amylose, and they are alpha in nature. The nature of these linkages, they are alpha in nature. So, and tentative structure was also that since the maltose are present there, then it was found that they may be linear in the shape. So based on these assumptions, a tentative structure of maltose was this alpha amylose was formed, and in this case we can say that again they were having a number of units of maltose, you can see here, and they are connected through, if you see this, the position of oxygen and the position of O H in the glycosidic linkage, we see that they are having 1,4 connections. They are connected. This is the carbon 1, it is connected to the carbon 4. 1 2 sorry 1 2 3 and 4. So we can see that there is a connection linkage between carbon 1 and carbon 4, and since you can see the position of the glycosidic bond, it is alpha. When we so based on these assumptions, we say that they are having a linear structure. When they are having a linear structure, there is 1,4 type of linkages. One, the glucose molecules are present only, the glucose molecules are the main constituents of this. Then there is 1,4 linkages, that is glycosidic linkages are there, and they are alpha in nature. So based on these tentative, when they were used, diastase, beta diastase was used for enzyme hydrolysis, we are getting the maltose as the main constituent, the products, and when it was doing the acid hydrolysis was done, the main constituent unit was glucose. So it was confirmed from this that the linear structure, it must have a linear structure, and then this linear structure was further confirmed when hydrolysis of methylated alpha amylose was done. Only two products were obtained. One is 2,3,6 trio methyl D-glucose and 2,3,4,6 tetra O methyl D-glucose. So only 0.3% of 2,3,4,6 tetra or methyl D-glucose has been obtained here. That shows that the chain length should be around 300 to 350 units, which is there. And then this also shows that, since we can say that when it was methylated, only the carbons which were having free hydroxy groups, the OH groups which were free in this alpha amylose were methylated. So we can say that the carbon 2, the hydroxy group as carbon 2, 3 and 6, they were free in alpha amylose, and they were methylated. So the linkage possibility is either at the carbon 1,4, because we are having the free groups at one CHO group, there the free groups, and then the free hydroxy group at carbon 4 and the free hydroxy group at carbon 5. So we say that it may be the 1,4 linkage, or we can say that it is a 1,5 linkage. 1,5 is possible only if it is having a furanose form, and 1,4 is possible only if they are having the pyranose form. Since we say that based on the hydrolysis, again we say that they are having pyranose form, so the linkage which is there must be a 1,4 linkage. So the second thing is, like, when 0.3% of 2,3,6 tetra O methyl D-glucose have been formed, it confirms that alpha amylose must have a chain with glucose units of 300 to 350 units, and that was supported by the molecular weight determination using various physical methods. Then again, this molecule is having a linear structure. It was confirmed by having because this alpha amylose that has a characteristic of linear structures, it shows the high positive rotation. That is the character of the linear structures, to have the high positive rotations. So it was confirmed that now alpha amylose is having a linear structure, and it is having a 1,4 linkage, and they are alpha in nature, and then the glucose is the main constant of these molecules. Further, it was shown that when iodine solution in the iodine solution of this alpha amylose was having blue color, and it was because of the adsorptive property of this, and we can say that the iodine was present because of adsorption property of the alpha amylose. We say that this blue color was there, and with iodine gives a blue. The color is ascribed to entrapping of iodine molecules between the chains of the amylose. This was actually confirmed by the X-ray studies. When X-ray studies of alpha amylose iodine complex was done, it was found that alpha amylose is not a it is a straight chain, it is linear chain, but it is not a straight chain, but it forms as in helix, like DNA molecule. It forms as an helix, and a single stranded. DNA is a double stranded helix, this is a single stranded helix, and it was seen that the iodine lies along the axis of the helix, that iodine which is entrapped in this, and this entrapping of the iodine, that as I said that it is an adsorptive property, so that adsorption of this the entrapping of the iodine within the helix along the axis of the helix gives it a blue color. So we can say now this molecule is actually having a linear structure, but the chain is not straight, that chain is helical in nature. Then acid hydrolysis, amylopectin, when acid hydrolyzed, it again gives the D-glucose molecule. That again shows that the main constituent of this is D-glucose. So we can say that both alpha amylase and amylopectin, they are having the D-glucose as main constituent. That is why when the starch was hydrolyzed, around 98% of D-glucose was obtained, because the starch, which is starch, is made up of alpha amylose and amylopectin. Alpha amylose and amylopectin, and both alpha amylose and amylopectin are having glucose as the main constituent. So in both the cases we can say that they are made up of glucose, and the whole molecule, that is the molecule of starch, it is made up of glucose. So it is a monosaccharide, which is the homopolysaccharide, which is having the monosaccharide unit. Glucose is the main monosaccharide unit which is present in the starch. So we say amylopectin, again it gives the main component, that is D-glucose. When enzyme hydrolysis was done, in enzyme hydrolysis, when they were hydrolyzed using beta amylase, it has been found the two constituents which are present there was maltose and limit dextrin. So when we say the maltose, again we say that that is an established fact that it is having a 4 linkage, and that means that the amylopectin is again having a 1,4 linkage, that is alpha in nature. But limit dextrin is there, that shows that this molecule is not a straight chain or a linear chain molecule. Had it been a linear chain molecule, the maltose would have been the only product. So we say that there are some branched points. Branch points are present in the amylopectin. So that indicates that amylopectin is not a linear molecule. So based on this, when methylated amylopectin was hydrolyzed, we had obtained 3 products. It was 2,3,6-trimethyl D-glucose, 2,3,4,6 tetra-o-methyl D-glucose, and 2,3-di-o-methyl D-glucose. So as previously we said that if there is the presence of 2,3-di-o-methyl glucose, that indicates the dimethyl glucose indicates the presence of a branch point, and in this case we can say that the branch point, the glucose which is present at the branch point, it is having only 2 hydroxy groups free. One is carbon 2 and carbon 4. 2 carbon 2 and 3 which have been converted into methoxy groups. So we can say that that branch point lies, because we already say that there is a 1,4 linkage, and this the carbon 5, the hydroxy group at carbon 5, this is actually involved in pyranose form, formation of the pyranose form. So we say only the glucose which were the linkage which were present is 1,4 linkage, that is carbon 1 and carbon 4 are involved in pyranose form, they are involved in the linkage. Then the free hydroxy group at carbon 6 indicates that the branch point is at carbon 6. So we say that this it is having a branched structure and the branch point is at carbon 6. Now we can see again that there is equal proportion of the two, that is 2,3,4,6 tetra-O-methyl D-glucose and 2,3-di-O-methyl D-glucose have been obtained. That indicates that each branch point has an and group present there, that is non-reducing N group is there. With each N group there is a branch point. Now 2,3-tri-O-methyl D-glucose, again it shows that the linkage which are present in it, that should be, that linkage is again 1,4 linkage, and so from this we can say that tetramethyl glucose corresponds to a chain length of 25 glucose units, because we can say that the 4% of tetra 2 3 4 6 tetra OD glucose have been tetra O D tetra O methyl D glucose has been obtained. So that is the at the non-reducing end side, and the first molecule which is present on the non-reducing end side, that gives us 2 3 4 6 tetramethyl D glucose has been produced, and that is around 4%. That indicates that around 25 glucose units are present in the amylopectin chain, and that has been further confirmed by using the sodium periodate oxidation. Now this was using the oxidation method. So but when the osmotic pressure method has been revealed, that when molecular weight was calculated using the osmotic pressure, it was revealed that around 500,000 the molecular weight of these amylopectin is 500,000, that corresponds to around 3,000 glucose units. So it was like there is a huge difference, about 25 glucose units and around 3,000 glucose units. Now the another point that was confirmed here was actually when we say that there is the presence of around 3,000 glucose units, which was not given in the first one, that is using the sodium periodate oxidation method. That indicates that it is having a branch structure, because in branch structure there is the large number of glucose units is present. Then it was further that the similar quantity of di and tetramethyl D glucose, that reveals that for a chain point in each end group, there is a chain point in each end group, and the formation of dimethyl glucose reveals that amylopectin has a branched structure, and the branch chain is linked through carbon 6, as I said in the previous slide, that since we are getting only 2 3 dimethyl di-O-methyl D glucose. So that means the free hydroxy group at 6 indicates that the branch point, they are connected through 1,6 linkage. So the evidence for branch chain structure of amylopectin is that amylopectin acetate does not form fibers. That is essential one, like as in case of in case of starch alpha amylose, we say that they form the fibers, or in case of cellulose, we say that the cellulose acetate, they form the fibers. That is a primary character of the linear molecules. So we say that since there is absence of fibers, it does not result in the formation of fibers. We say that this molecule has a branch structure. Second is amylopectin diacetate hydrolysis produces only 50% of maltose, that is some block points are not attacked by the enzyme. So that block point is a branch chain block point, which is at carbon 0.6. So we say that the 1,6 linkages are not attacked, 1,6 linkages are not attacked by the diastase, the enzyme diastase, and only the 1,4 links are attacked by the enzyme diastase. That is why 50% of the maltose was obtained, and limidextrin was obtained. The 50% of limidextrin was obtained. So because we say that in limidextrin there is the presence of 1,6 linkage that was not attacked by the diastase enzyme. Now absence of orientation of the molecules, when the solution of this amylopectin solution was treated, was observed that it was observed that this solution does not show the orientation of the molecule in the direction of flow in concentric cylinder technique. So the absence of this orientation indicates again that this molecule is not linear, it is a branched chain molecule. And then as we said that the 2,3-dimethyl glucose and 2,3,4,6 tetra-o-methyl D-glucose molecules have been obtained. The 2,3-dimethyl glucose indicates that it is a branch chain structure, and it shows that for each end group there is a branch point, and that is why we say that these two molecules are equal. So based on this, partial hydrolysis was done on the amylopectin, and it was found that in partial hydrolysis it was found that two molecules have been obtained. One, when partial enzymatic hydrolysis was done, one was obtained as maltose, so the maltose shows 1,4 linkage, and the second was isomaltose. Isomaltose shows the 1,6 linkages. You can see 1, 2. So they show the 1,6 linkages. This 1,6 linkage indicates that the branch point lies again at the carbon 6 here, and this is the branch point, and 1,6 linkages and 1,4 linkages. So based on this, the structure of amylopectin was given, and it was understood that the amylopectin is having a structure that is a branched structure. The main chain, that is the linear chain, is having 1,4 linkages, and those 1,4 linkages again, if we observe here that the oxygen here and this position, we can say that the 1,4 linkages, they are beta in nature, they are alpha in nature, and then there is again a 1,6 linkage which makes it a branch point. So the carbon 6, in some cases it is a branch point, and 1,6 linkages are there. So we are having two types of linkages. One is 1,4 which is alpha in nature, and then it is 1,6 again, it is an alpha in nature. You can see again the 1,6, it is alpha in nature. So these are the main molecules. This is the structure of amylopectin, and we say that the starch, which is having now two molecules, one is alpha amylase and then amylopectin, they form the starch molecule. So we have discussed here in this lecture, we have discussed the structure of both the molecules. Thank you.